Okay, so today we will continue our discussion of the nucleophilic substitution reaction. We've introduced the concepts of basicity and nucleophilicity. We've mentioned that basicity is a thermodynamic property. It's related to the equilibrium constant of an acid-base reaction, whether or not it's favorable or how favorable it is. And the concept of nucleophilicity, in contrast, is a kinetic phenomenon. It relates to how rapid a given nucleophilic substitution reaction will occur. Because kinetics and thermodynamics do not have to be related to each other, there are some scenarios in which basicity and nucleophilicity are correlated, and others in which they are not. And so we will explore that today. In that context, we'll talk about the effects of solvents on nucleophilic substitutions. And then we'll conclude with a discussion of the mechanism of, or mechanisms of nucleophilic substitution reactions. So there are many cases in which basicity and nucleophilicity are correlated, meaning that if we are comparing two different nucleophiles, and we're asking ourselves which one is a stronger nucleophile, meaning which one will undergo a nucleophilic substitution faster, in these three cases, the stronger base will be the stronger nucleophile, or the weaker base will be the weaker nucleophile. Or if we're comparing more than two, we could put them in order from strongest to weakest in terms of basicity, and that trend would be the same for nucleophilicity. So I've written the three cases where they're correlated on the board. The first one says that if the nucleophilic atom is the same, if it's both oxygen or both nitrogen, so if that nucleophilic atom in our two different nucleophiles is the same, then the stronger base is almost always the stronger nucleophile. You'll notice that in organic chemistry, we have a fair amount of exceptions. So we can't say always the stronger nucleophile. In about 10 or 15 minutes, we'll show you an exception to this. But in the vast majority of cases, I will say that if you have the same atom as the nucleophile in your two different nucleophiles that you're comparing, then the stronger base will be the stronger nucleophile. Our second principle is that a negatively charged nucleophile will always, this one is always the case. I don't know of any exceptions to this one. The negatively charged nucleophile will always be stronger than its conjugate acid. So if you're comparing two different species and they're related to each other as a base and its conjugate acid, the base, which is a stronger base, will be the stronger nucleophile. And then our third principle is that when we are comparing bases where the nucleophilic atoms are in the same row of the periodic table, we're going across the periodic table, then the stronger base will be the stronger nucleophile. Any questions? So let's look at some examples. And these examples will be in the context of iClicker questions. So we actually have three iClicker questions in one here. So you're glad you're here and you're glad you have your iClickers today. So go ahead and get those out. You can talk to your neighbors. And right now we're answering question number one. We're comparing these two species. We're using these three principles. The three principles are still on the board to help you. And we're deciding which of these two species is the stronger nucleophile. So go ahead and discuss this and answer number one. All right, are there any more answers? There we go, 22. I'll give you about 5 or 10 more seconds to see if there's any more answers out there. Going once, going twice. Okay, we'll go ahead and stop number 1 now. And then when I open it up, we'll be on number 2. So now we're comparing these 2 species and using one of our 3 principles to decide which is the stronger base. Okay, let's come up with our final answers in the next 10 seconds or so. Okay, we have one more answer to come in, it looks like. Any more answers? Going once, going twice. All right, I guess that's all we have for this one. Okay. Now number 3. Okay, let's try to come to a conclusion here in the next 10 seconds. Okay, that looks like all the answers. I'll go ahead and close it off. Okay, so I'm looking for a volunteer to raise their hand and tell us which one they chose as the stronger nucleophile for question 1 and why. Which of those principles you use to come to that conclusion. Okay? Okay, B had a negative charge, and so you applied principle number 2, I'm assuming, right? That a negatively charged nucleophile will always be a stronger nucleophile than its conjugate acid. That's what that means, yes. So you can see these examples here illustrate, each one of them illustrates one of these principles. You could have also applied number 1 if you wanted to, because both of those have an oxygen as the nucleophilic atom. But this number 2 is actually more specific than number 1. We would say here that because these are related as a base and its conjugate acid, that the hydroxide is a stronger nucleophile than water. Okay? All right. Who would like to raise their hand and explain their reasoning and their answer for number 2? Don't be shy. Yes, okay, Minnie? Okay, rule number 3, yep. Okay, so nitrogen and oxygen are in the same row of the periodic table. They're right next to each other. So we can conclude that because they're in the same row, the stronger base will be the stronger nucleophile. And why is NH2 minus a stronger base than hydroxide? That's a little tougher question. Electronegativity, okay, which is more electronegative, nitrogen or oxygen? Oxygen is more electronegative. So the oxygen holds on to its electrons more tightly, and so they're less available to function as a base than the electrons or the lone pairs in NH2 minus. Okay, that's the shortcut way of concluding that NH2 minus is a stronger base than hydroxide. If you didn't recognize it that way, then you could make the conjugate acids and compare their relative acid strength. And you'd probably recognize that water, H2O, is a stronger acid than ammonia, NH3. And that would lead you to conclude that the one with the weaker conjugate acid would have to be the stronger base. Okay, so a couple ways to come to that conclusion. Basicity and nucleophilicity are connected because they're in the same row of the periodic table. Okay, who would like to answer number 3 for us and explain the reasoning? Claire? Okay, so you're saying that acetate is more stable than hydroxide. Does that make it a stronger base or a weaker base? That actually makes it a weaker base. So if that negative charge is delocalized, it's going to be less reactive, and so it's going to be more stable. It's conjugate acid, so the conjugate acid of this is acetic acid, right? Conjugate acid of hydroxide is water. Which is a stronger acid, acetic acid or water? Acetic acid is a stronger acid. And so we would say that acetate is a weaker base because it's more stable. So your reasoning was correct, but unfortunately you got the wires crossed between your reasoning and getting to your final answer. I know you weren't alone in that, as I saw the results there, but it's just a reminder to we have to be very careful in recognizing the relationship between stability and reactivity of our bases. The ones that are more stable are going to be less reactive as a base. Their negative charge is going to be delocalized, and that's going to make them less reactive. Okay? So I think you're finding as we go through these examples, and a couple more that we'll do today, that we cannot forget about acid-base chemistry. I warned you about this when we were studying chapter 2. I said that acid-base chemistry is fundamental. The principles are fundamental and will continue throughout the class. And so we're seeing today how acid-base chemistry applies to nucleophilic substitutions. Question? Okay, so cases that don't follow these rules. Yeah, so you're on target because in most cases, basicity and nucleophilicity are correlated. However, there are 2 main exceptions that we're now going to talk about where they're not correlated. The first one is steric effects. So I've drawn for you 2 bases here. These are the conjugate bases of alcohols. They're known as alkoxides. The one over here is called ethoxide. Ethoxide is the conjugate base of ethanol. The one I've drawn here is called tert butoxide. Tert butoxide is the conjugate base of tert butyl alcohol. I've also drawn for you the pKa's of the conjugate acids. So based on these pKa values for their conjugate acids, which one is a stronger base, ethoxide or tert butoxide? Tert butoxide is a stronger base. It has a weaker conjugate acid. Okay. What's the difference in basicity based on these numbers? How much stronger is this than that? 100 times, right? 2 orders of magnitude. So definitely a measurable difference. Tert butoxide is a stronger base, 100 times stronger base than ethoxide. So normally we would say it's a stronger nucleophile, but because I said this is an exception, you've probably figured out that ethoxide is a stronger nucleophile than tert butoxide. Why? Why would ethoxide be a stronger nucleophile than tert butoxide? Claire?
Because tert butoxide is really crowded, and so it can't reach the carbon that it's trying to get.
It cannot attack the electrophilic carbon because of its bulk or its steric hindrance. You're exactly right. Okay, so we see that tert butoxide is a much larger molecule. That this oxygen is attached. So this is the conjugate base of a tertiary alcohol, meaning that this carbon has 3 alkyl groups attached. This is the conjugate base of a primary alcohol, meaning that this carbon bonded to the oxygen only has 1 carbon attached. So this one has more alkyl groups, more R groups, bulkier, bigger. And the tetrahedral carbon of an alkyl halide is bulky itself. It has 4 groups pointing out in all possible directions. And so for the bulkier nucleophile, it takes a heck of a lot longer time to approach that sterically hindered tetrahedral carbon than it would take the smaller nucleophile of ethoxide. Okay, so steric hindrance affects nucleophilicity. And when you have a very bulky nucleophile, a large nucleophile, it's going to be a weaker nucleophile than a small nucleophile. Okay? Question?
So you're saying that the one on the right is less nucleophilic?
Yes.
Because atoms have a hard time approaching it because of the extra carbon around?
Yeah, it has a hard time approaching the, we typically think of this as approaching the electrophile because we always think of the electrons flowing from the nucleophile to the electrophile. But yes, you're going to have a collision between this and the alkyl halide in order for a substitution to occur. And it's going to be hard to have that collision in the right orientation because they're big. Okay? It would be like 2 people in big sumo suits trying to hug each other, basically. So, yes.
It seems like to a certain point this could be objective. Is there any rule to tell us how we can know if this size of an alpha group is going to cause steric hindrance enough to be less nucleophilic?
Sadly, there is not a general rule that we can use. We will say that tert butoxide is a very, very special reagent. Okay? Tert butoxide is a strong base, but it is a weak nucleophile. And there aren't that many species. Most strong bases are strong nucleophiles. And so the fact that tert butoxide is a strong base and a weak nucleophile makes it very special. When we get to chapter 8, we'll see why. Okay, in chapter 8, we'll be learning about elimination reactions. And tert butoxide is very special in eliminations because of this property. So nucleophiles that are intermediate in size between these will have intermediate properties, right? They will be weaker nucleophiles than this, but stronger nucleophiles than that. But we don't have like a hard and fast dividing line to say this is sterically hindered and this is not. You can compare 2 things or you can compare 3 things and see which one is more hindered than another, but we don't really have a threshold or a dividing line.
So typically we won't be asked to decide if one or the other is better nucleophile. We would just be asked to say this one's more sterically hindered than that.
That's too specific. That's putting too many words in my mouth, so I'm not going to go that far. But what I will say is you will be able to answer any question that I ask. That's the one concession I'll make. Yes?
So I was just wondering if terbium oxide were to approach just a proton, would it be stronger nucleophile than if it were to approach the bigger?
Okay, so that's a good point and leads right into the next thing we're going to talk about. So if terbium oxide is approaching a proton, then it's functioning as a base rather than a nucleophile, because if it's donating its pair of electrons to a proton, it's acting as a Bronsted-Lowry base. Okay? And basicity is not affected by sterics. Okay? This is a stronger base than that. We're not going to get into the reasons why right now. We haven't learned the reasons why it is. But it's a stronger base and it's more hindered. So we can see that basicity is not affected by steric hindrance, whereas nucleophilicity is. The reason is that a proton is the world's smallest nucleus. And so it doesn't matter how big or small your base is, it's going to pluck a proton out of a molecule rapidly. Acid-base reactions are typically the fastest reactions we encounter in organic chemistry. So they're going to proceed regardless of how big or small the base is. They're always going to be fast because all you're doing is plucking out the smallest nucleus that we have. So steric hindrance does not impact basicity. That's why we don't have to think about kinetics. When we're thinking about acid-base reactions, in most cases, we can ignore kinetics because they're all going to be fast. So when we're thinking about the property of basicity, we can just focus on thermodynamics, whether or not the reaction is thermodynamically favored. In an acid-base, a Bronsted-Lowry acid-base reaction, you're always going to reach equilibrium rapidly. The only question is, when you reach equilibrium, does it favor the reactants or the products? So that's why basicity is a thermodynamic property, not impacted by steric hindrance, because there's really negligible differences in rates. They're all going to be fast. Whereas nucleophilicity, because your nucleophile is approaching a tetrahedral carbon, that carbon is much more crowded than a proton. Now, sterics does matter, and now there are differences in reaction rates where smaller nucleophiles would react faster than larger nucleophiles. Okay? Good question. Any other questions on our steric effect? So you can see this is the exception I was referring to when I wrote the phrase almost always here. We have the same nucleophilic atom, oxygen in both cases. But in this case, the weaker base is the stronger nucleophile because the stronger base is too bulky, too sterically hindered. Any questions? Okay. Our next exception to the correlation between nucleophilicity and basicity deals with solvents. So in a nucleophilic substitution reaction, we will always be using a polar solvent. Our nucleophiles, in most cases, are salts. And so we have to have a highly polar solvent to dissolve the salt and to dissolve the alkyl halide. Some cases they're not, but they're still very polar molecules. But there are two classes of polar solvents. The first one we'll talk about is the polar protic solvent. Polar protic solvents are capable of hydrogen bonding. So the first polar protic solvent that probably comes to mind is water. Water is not great at dissolving alkyl halides, so we would more commonly use alcohols. Alcohols are cousins of water, but they have alkyl groups attached to the oxygen, like methanol or ethanol. And then we could also use carboxylic acids as a polar protic solvent, such as acetic acid that I've drawn for you here. So if we were to dissolve a nucleophile that comes as a salt, we'll use sodium bromide in this case. Bromide will be our nucleophile, but we're delivering it to the reaction as sodium bromide. Can our sodium cation be stabilized by intermolecular forces with polar protic solvents? It can. So if we were to dissolve this in water, which atom of the water would be interacting with our sodium cations? The oxygen would. The oxygen has the lone pairs. Let me draw the lone pairs. So we would have an arrangement such as this of water molecules surrounding our sodium cation. And what would we refer to these interactions as? These are ion-dipole interactions. We learned that term in chapter 3. We can't forget the material in chapter 3 either. Okay? So our sodium cation in a polar protic solvent is solvated. Solvated is a term we use for stabilizing interactions with solvent. It's solvated by the polar protic solvent due to these ion-dipole interactions. Okay? Now, what happens to our anion? Can our anion be solvated by water molecules? Yeah, what atom of our water would be interacting with the bromide? Okay, the hydrogen atom, the proton. So it would look like this. And what do we call these interactions? What do we call them? These are also ion-dipole interactions. Okay. Be careful not to call them hydrogen bonds. The book actually makes a mistake and refers to them as hydrogen bonds. They're not hydrogen bonds according to the book's own definition of hydrogen bonds, but they are strong ion-dipole interactions. Okay, so these are strong ion-dipole interactions between these protons and the bromide. Okay, so we would say that the bromide and any negatively charged nucleophile would be solvated in a polar protic solvent. Now, if we're comparing two different nucleophiles, we have a big nucleophile and a small nucleophile. Which one would be more effectively solvated? Big or small? Would it be easier for solvent to surround a small anion or a large anion? A small anion would be easier for the solvent molecules to surround than a large anion. So if we're looking at the halogens, or the halides in this particular case, we would say that a fluoride ion is going to be more solvated than a chloride ion, which in turn would be more solvated than the larger bromide, and the iodide would be the least effectively solvated. You're just going to have that smaller anion more efficiently surrounded by your water molecules. Question? There?
When they surround the small anion, wouldn't there be some like repulsion between the hydrogens surrounding it, which would make it like less solvent?
So the water molecules, that's a good question. They're not really going to get close enough together for that to be an issue. There's going to be, and that would be, you'd have a similar problem whether it was big or small. And it's just going to be easier to get the water molecules around the smaller atom as opposed to, or the smaller ion as opposed to the larger ion. So do you think a more solvated nucleophile would be stronger or weaker than a less solvated nucleophile? Will solvation make something a stronger nucleophile or a weaker nucleophile? Weaker nucleophile. Why? Let's have a raise of hand and an answer here. Yes, please.
Well, the more solvated it is, the less available it is to react.
Exactly. The nucleophile will have to shed those intermolecular forces to the solvent before it can act as a nucleophile. The solvent's basically going to be a barrier between the nucleophile and the alkyl halide. So a more efficiently solvated nucleophile will be a weaker nucleophile. Therefore, if we're looking at the halides, going down the periodic table, we would say fluoride in a polar protic solvent is going to be a weaker nucleophile than chloride, which will be a weaker nucleophile than bromide, and then iodide would be the weakest of them all, okay? And that is due to fluoride being the most efficiently solvated, and then iodide being the least efficiently solvated in a polar protic solvent, okay? Which of these four halides is the most basic? The earlier group struggled with this as well. So remember, you cannot ignore chapter 2. Acid-base chemistry is permeates the whole class. Yes? Okay. Your reasoning is correct, but your conclusion is backwards, right? See, the same problem that Claire did, right? Your reasoning is correct, but the conclusion was backwards. So you're saying iodide is more stable than fluoride, right? Iodide is larger than fluoride. They both have the same charge on them. And so you have that negative charge spread out over a larger area with iodide than you do with fluoride. So iodide is more stable, and the more stable base is less basic, right? The less stable base is going to be more reactive, more basic, okay? So fluoride is more reactive, more basic than chloride, than bromide, than iodide. So this trend here is opposite of basicity. We have the strongest base as the weakest nucleophile, the weakest base as the strongest nucleophile. So this is exception number 2 to our correlation between basicity and nucleophilicity. When we are using a polar protic solvent, solvation makes our stronger bases weaker nucleophiles. This makes a difference when we're comparing bases from the same column of the periodic table. In the same row, solvation would be very similar because we would have similar sizes. Okay? But in the same column, the sizes are very, very different. And so our smaller, more basic nucleophiles are going to be more efficiently solvated. Okay? Because they're more efficiently solvated, they're less reactive, less nucleophilic. Okay? So polar protic solvents, exception number 2 to our relationship between basicity and nucleophilicity. So our second category of solvents is polar aprotic. So polar aprotic solvents are incapable of hydrogen bonding. Meaning they do not have an OH or an NH. So a couple of examples. This polar aprotic solvent is called acetone. This one is a little unusual. I'm going to draw 2 different resonance structures. We see it drawn in either of these 2 resonance structures sometimes. This one is called dimethyl sulfoxide, or DMSO. Its true structure is a hybrid of these. And if you're wondering why there's no formal charge on this sulfur that has 4 bonds, when you're in the 3rd row of the periodic table, the rules for formal charge are very different than they are when you're in the 2nd row. So we're not going to address that. But just recognize that DMSO is a polar aprotic solvent because it has no OH or NH, but it has polar bonds. So it can dissolve polar molecules. Another one, DMF, this stands for dimethyl formamide. This one here is called acetonitrile. And then we have a cyclic ether, which is tetrahydrofuran, or THF. Notice we use a lot of abbreviations when we have long names for these species. But what they all have in common is they are polar, but they are unable to hydrogen bond to another molecule of themselves. So they are polar and aprotic. So if we were to dissolve a salt, where the anion is a nucleophile, in a polar aprotic solvent, could we solvate the cation? Let's take sodium again. Could we solvate a sodium cation with acetone molecules? We could. What atom of the acetone would be pointing towards the sodium? The oxygen would. Okay. Okay. So the partial negative end of our dipole of our acetone molecule, the oxygen atom, would be solvating our sodium cation. Okay. What about our bromide? Could we solvate our bromide in a polar aprotic solvent? The answer is not very well. We do have a partial positive carbon here, but the interactions between that partial positive carbon and the bromide are much, 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 much weaker than the interactions we would have between a proton and that bromide. Okay? So we say that in a polar aprotic solvent, we have a naked anion. That's just a way of saying that it is not solvated. It's not stabilized by intermolecular forces to the solvent. And so that naked or unsolvated anion is going to be more reactive than a solvated anion. It does not have to shed those intermolecular forces between itself and the solvent before it can act as a nucleophile. It can act directly as a nucleophile. Okay? So, in a polar aprotic solvent, because we do not have solvation of our anion, we do have a correlation between basicity and nucleophilicity. Because we don't have to consider or worry about solvation, we would say that in a polar aprotic solvent, our stronger base will be the stronger nucleophile. So fluoride would be the stronger nucleophile in a polar aprotic solvent, such as acetone, followed by chloride, bromide, and iodide. Okay? So polar protic solvents invert the relationship between basicity and nucleophilicity because they solvate the smaller anions more effectively, which are more basic than the larger anions. Whereas in polar aprotic solvents, we do not have solvation of the anions. We only have solvation of the cations. And so we preserve the relationship between basicity and nucleophilicity. Questions? So this means it's important for us to be able to identify a polar protic solvent versus a polar aprotic solvent to see the impact that it may or may not have on nucleophilicity. So again, two exceptions to the relationship between basicity and nucleophilicity: steric hindrance and polar protic solvents. Question?
For polar protic solvents, do they have to be capable of, they do have to be capable of hydrogen bonding with themselves, right?
Polar protic, yes, have to be able to hydrogen bond to themselves. All right, so we have a helpful table in the book showing us common nucleophiles that we will encounter. You can have a variety of nucleophilic atoms as we see here. And the book has divided them up into negatively charged nucleophiles and neutral nucleophiles. This is helpful because by the end of the chapter, you'll see that it's important for us to be able to classify nucleophiles as being either strong nucleophiles or weak nucleophiles. And we're going to consider all of our negatively charged nucleophiles as strong nucleophiles unless, we can't just say all, we do have to say unless, sorry about that, unless they're sterically hindered. Right up here at the top of the board, we see we have a negatively charged species that is a weak nucleophile because of its steric hindrance. Okay, so if we have something that's the same size as tert butoxide or bigger than tert butoxide, we will say that's a weak nucleophile, regardless of whether or not it has a charge. But with the exception of steric hindrance, all of our other negatively charged nucleophiles will be strong nucleophiles. Now, of our neutral nucleophiles, they're going to be weak nucleophiles with the exception of ammonia, NH3. NH3 is our strongest nucleophile of the neutral ones, and we're going to consider it as a strong nucleophile. Nitrogen is our least electronegative atom with a lone pair, so that lone pair is the most available, most basic, most nucleophilic. And NH3 is the smallest of any of these nitrogen containing species. And so therefore, NH3 is a strong nucleophile. When we have an R group attached to a nitrogen, like this species right here, if it were small, it could be strong. If it were bulky, it could be weak. So we're not going to worry about that too much, whether it's weak or strong. We're just going to say that negatively charged nucleophiles, unless they're sterically hindered, plus ammonia, those will be our strong nucleophiles for the class. And all other neutral nucleophiles other than ammonia we'll consider as weak. Any questions? Again, by the end of the chapter, you'll see why this matters, because it affects the types of substitution reactions that the nucleophile can undergo. All right, let's talk now about possible mechanisms by which substitution can occur. So we could have a concerted nucleophilic substitution where our nucleophile reacts with our alkyl halide. And these are not methyl groups. These are just three valences, some combination of hydrogens and alkyl groups. But in our concerted substitution mechanism, we form a new bond between the electrophilic carbon of our alkyl halide and the nucleophile at the same time as we are breaking the existing bond between the carbon and the halogen leaving group. So we end up with our product, our halide leaving group departs, and we can write a rate equation for this reaction. I'll start it out for you. Rate equals a constant times something. What's going to go after the constant in this rate equation? Concentration of the nucleophile. Okay, anything else? The alkyl halide. We'll just call that Rx in this particular case. So is the rate equation for the concerted nucleophilic let me back up. What is the order of the rate equation for the concerted nucleophilic substitution? It is second order. Okay? Based on the definition we learned in chapter 6, this is a second order reaction. We add up the exponents of the concentration terms in our rate equation, and we see it's second order, first order in nucleophile, first order in alkyl halide. We also could have substitution occur via a stepwise mechanism. In the stepwise mechanism, the bond breaking would precede the bond formation. We would generate a carbocation intermediate. That carbocation intermediate would react with our nucleophile to go on and give the final product. Okay? So to write a rate equation for this reaction, we would have to determine which of these two steps would be the rate determining step. Which do you think it would be, the first step or the second step? The first step. Why? All we're doing is breaking a bond. We're going to have a very high energy barrier to break a bond. And so that's going to be our rate determining step or our slow step. So let's write our rate equation. Rate equals a constant times what? Concentration of the alkyl halide. Why are we not including the nucleophile? It is not participating in the rate determining step. So what is the order of our stepwise mechanism? It is first order. Okay. So this is very helpful. Well, before I go there, why are we not considering a second stepwise possibility where bond formation would precede bond breaking? That would violate the octet rule. So we can throw that out. We know that there's no way to form the new bond at our electrophilic carbon before we break it. The best we can do is simultaneous. Okay? So these are the only two possibilities. And the fact that they're the only two possibilities gives us a great opportunity to distinguish between these mechanisms. All we have to do is run our substitution reaction at different concentrations of the nucleophile. If the rate changes, then we know it has to be the concerted mechanism. If the rate does not change, then we know it has to be the stepwise mechanism. Okay, so this is very convenient, and it allows us to easily determine which of these mechanisms is operating. Okay, so we could take acetate ion. We know it's a weaker nucleophile than hydroxide from our eye clicker, but it's still a strong nucleophile, negatively charged. We can react it with bromomethane. And we get this product, which is an ester. And we have bromide ion. And what we find is that this particular reaction is second order. Okay, so that tells us that this substitution reaction is occurring via our concerted mechanism. However, we can take the same nucleophile, we can react it with a different alkyl halide, in this case tert-butyl bromide. Nucleophilic substitution occurs, but in this case, it is a first order reaction. So this one must be occurring via the stepwise mechanism. The rate of reaction only depends on the alkyl halide. It does not depend on the concentration of the nucleophile in this case. So that tells us that we have two different mechanisms, the concerted and the stepwise, and either one can operate depending on the nature of the alkyl halide, and in some cases, the nature of the nucleophile. So let's talk for a couple minutes about the second order or the concerted mechanism. We refer to this as the SN2 mechanism. Okay? The S stands for substitution. The subscripted N stands for nucleophilic. And the 2 stands for bimolecular. This is a single-step concerted mechanism. It might seem confusing or counterintuitive that we have a 2 here when it's a one-step process. What that 2 refers to is bimolecular or second order. It has second order kinetics. Okay? So it's concerted. We have an energy diagram here for this reaction. Question? Yes. Yes, it means if it's second order, it means you have 2 molecules participating in your rate determining step, so that's bimolecular. So we see here reactants, products. We notice that this particular substitution is exothermic. Notice that our leaving group is less basic than our nucleophile, so that makes it exothermic. At our transition state, You can see we have a partial bond that is forming between the carbon and the oxygen. We have a partial bond that is breaking between the carbon and the bromine. We have a partial negative charge on the oxygen that's decreasing at the transition state. Partial negative charge on the bromine that is increasing at the transition state. Okay? So one-step reaction, we only have one transition state in our SN2 reaction. Last thing we'll mention is stereochemistry. If we have a chiral alkyl halide, if the substitution reaction is occurring at a stereocenter, then what happens to the stereochemistry in the product? Is it going to be the same as it is in the reactant? Is it going to invert? Or is it going to give us a mixture? Okay, this is an important question. And there were some chemists many years ago in England who answered this question. They took a single enantiomer of this alkyl halide. This is 2-bromooctane. And it is the S enantiomer. And it rotates plane polarized light in the positive direction. That was all known. They used sodium hydroxide as their nucleophile. So they got an alcohol, and what they found was that the orientation of the stereocenter had inverted. They made R to octanol. We haven't learned alcohol nomenclature, but it rotated plane polarized light in the opposite direction. These are not enantiomers of each other. They aren't even isomers of each other. But you can see the way I've drawn them that we have the opposite configuration at the new stereocenter compared to the old one. So what we see in SN2 reactions is inversion of the configuration. And we'll talk a little more about that when we get back together on Monday. Okay? So have a good weekend. Stay healthy and stay safe. And we'll talk about SN2 stereochemistry more on Monday.